Hey there, in this video we're going to be looking at electric potential as work done per unit charge. When we have charges that are of the same kind, we see that when we move the two charges towards each other, they experience a force of repulsion. So in both the cases, this is case 1 and this is case 2. When I have both the charges having the same nature, they end up experiencing a force of repulsion. That is, when like charges are moved towards each other, they need some external work, some force or some external work by the means of a force in order to move these charges towards each other. The same kind of example can be seen in the case of magnets. If we take two like magnets having the same pole, say I have a north pole and a north pole, and I move both the north poles towards each other, it is going to suffer some amount of repulsion. The same is seen with the case of south poles. When two south poles are brought towards each other, we see that there is some force of repulsion between these two magnets, and in order to get these two magnets to get together, we need external work to be done against this force of repulsion. The force of repulsion that we see in the case of like charges being pushed towards each other, or in the case of like poles of magnets being brought close together, is mainly due to the interaction of the electric fields of the charges, the electric fields of the charges and the magnetic fields of the magnet. So if I consider that let me consider positive charge of capital Q fixed somewhere in space. The electric field due to this positive charge is emanated outward in all directions radially. Let me consider a small unit test charge having charge Q naught. Say the distance between these two charges is a distance r. So now what do we have? We have two charges which are at a distance r from each other. Both of them are positive, meaning that the electric fields due to these charges are going to interact in such a way that when they are brought closer together, they need to be repelled. So obviously when I fix this test charge Q naught over here at a distance of r from my large positive charge capital Q, I had to bring it from some distance away from this charge capital Q. Let me think that this distance which I brought it from is very far away. That is at infinite distance. Infinite distance. The potential at this point, which is at infinite distance from my fixed charge capital Q, is considered to be zero. Why? Because the electric field basically dies out before it could reach this point. So the potential at infinite distance is considered to be zero, or also called as the zero potential. The zero potential. So my test charge Q naught has moved from infinite distance towards the charge capital Q fixed in space and has now occupied some distance r. Since both of them were positive, as I move from infinite distance to this distance r, the force of repulsion between these two positive charges is going to increase. Now imagine you have this test charge Q naught in your hand, and you have started from an infinite distance, that is basically a distance away from this large positive charge where you don't feel any repulsion, and you're moving this charge which is in your hand towards the point where it finally is at a distance of r. You will see that as you move closer, the force of repulsion on your hand keeps increasing. So you have some amount of force here repelling you in this direction, and at the same point as you come closer, this force keeps on increasing. The increase in force is shown by the length of the arrows. So you can understand at this point that since you are working against this force, the amount of work done by you in bringing this test charge Q to this point is basically the potential at this point. We can now define potential at a point as the work done I'm writing as WD, work done in bringing a unit test charge from infinity to that point, from infinity to that point. In our example, we took this charge to be a charge of Q naught positive, but much more smaller than the charge capital Q. So if I move from infinite distance to the distance of r, my potential will be equal to the work done in moving this distance from here to here divided by the magnitude of that test charge Q naught. We denote potential with the capital letter V. So V is equal to the work done per unit charge Q. We can also calculate what is the work done in moving a charge Q naught from infinity to a point where the potential is V. That work done would be Q, or in this case Q naught, into V. Let us now have a look at the unit of potential, that is the unit of potential. We've seen that potential denoted by the capital letter W is equal to the work done per unit charge. So what do you think would the unit of V be? The unit of V, that is potential, would be the unit of work done divided by the unit of charge Q. This is a no-brainer. The unit of work done is joule and the unit of charge is coulomb. Therefore, we say that the unit of potential is joule per coulomb or joule coulomb inverse. This is an SI unit of potential and it has been given a special name after the scientist Volta and denoted by capital V, which is read as volts. You must have used colloquially the term voltage whenever the voltage is fluctuating, etc. This is where the term volt comes from. So how is 1 volt defined? If 1 joule of work is done to bring 1 coulomb of charge from infinity to a point, that potential at that point is said to be 1 volt.